Having looked at the measures of location, we turn attention to now measures of variability. Variability kind of deals with the spread of the data. It also helps us compare, along with location, the relative variability between different series of data. So the most common measure of variability is the range, which is essentially the max minus the min value. And then we looked at the idea of percentiles, and we mentioned that 25th percentiles are called quartiles. So the first quartile is 25th percentile, the second is 58th, the third is 75th quartile. And the difference between Q3 and Q1 is called the interquartile range. So these two are like good broad measures of the spread of the data. But then more formally, we measure variability of a data series by its variance. Variance is essentially in terms of the population. That's what the sigma squared denotes. Suppose we knew the population. We had data on the entire population. Capital N is the population size, and mu is the population mean. Xi minus x is the deviation from the mean. So how far is each value from the mean? But if we add that up individually, we will be getting a number close to 0. So we squared that. So the square deviations around the mean, we add all of that up and we divide it by n. And that's what we call as variance. For sample, we adjust the denominator by n minus 1. So the sample standard deviation is essentially the squared deviations from the sample mean added up divided by n minus 1. So let's see how we can get these data sets or these statistics from JUMP as well. But before we get into those, the idea of skewness is an important idea that tells us kind of the spread of the data. So here we have 3 charts. The first one is symmetric, as we see that it is kind of like a bell-shaped curve with similar number of values to the left and to the right of the middle mass where we would have the mean, and in a symmetric data set, median as well. The second series is skewed to the left. Now, notice that skewed to the left means because there are a few trailing tails on the left, but the bulk of the values lie on the right. So a skewed to the left series is with some extremely low values, but bulk of the values lying on the upper end of the distribution. Similarly, skewed to the right, which is this graph, where we have a few trailing very large values, but bulk of the values are on the left-hand side. They are on the lower end of where the dataset value lies. So it's often confusing. Skew to the left does not mean the data is on the left. Skew to the left means that there are a few trailing low values, but bulk of the values lie on the right. And then skew to the right is the opposite, where we have some really high extreme values, but bulk of the values lie to the left. Now let's see how we can use JUMP to obtain these measures of variability that we had discussed. So here we have data set on market cap of a sample of companies, as well as their revenue in 2020, and the data is in billions of dollars. So we see that we have Apple and Microsoft, which are like above $2.5 trillion, but then rest of the companies have lower market capitalization. Travelers has $38 billion. So we will see measures of variation in this data. So we can start analysis by going to the Analyze platform, clicking on Distribution, and we move market cap to our y-axis. The default here, so sometimes in JUMP you might have a value clicked on, and then that always keeps getting highlighted all through the charts. So to clear that, I can right click and then click on clear. So now none of my data sets is selected, and then every point kind of is highlighted. So here what we're seeing is that JUMP has defaulted the bin width to 500 billion worth of bins, and then most of the data is under 500 billion, and then we have a couple of companies, as we saw, Microsoft and Apple, which have an extremely high market cap. So if we reduce the binwidth, we can do histogram options. We can actually make this have a horizontal display options, make it horizontal layout, so kind of more conventional as to what we have seen. And we can reduce the binwidth to maybe 25. Histogram options, set binwidth. We can see 25 billion. Again, we will have these two extremely high outliers. So once we look at it in a more conventional way, we see that this data is right skewed. We have a couple of values on the very high end, but bulk of the values lie to the left. We can also see our interquartile range and as well as our range. We go to summary statistics, customize summary stats, and then we can view variance. We can view our range and our interquartile range. So our range is 2912, which is the difference between the highest and the lowest. So the highest value is 2950 and the lowest value is 38. The difference between them will be 3912. Interquartile range, as we said, is the difference between the first and the third quartile. So our first quartile is 122.5 and our third quartile is 406.5, and the difference then is 284. So in terms of looking at the spread, range is looking at the high and the low, the highest and the lowest value, so it is prone to outliers. It shows a very high range. Interquartile range might be a better measure. We can see that we have these two outliers here. We will look at some formal ways of looking at outliers in just a little bit. Variance is given by 511287. And this is the square of the standard deviation, or the square root of variance is the standard deviation. Now, variance and its square root, the standard deviation, are two of the most important measures of spread of variability, and we will keep using them in the entire business statistics course and later on as well. These are two really important variables. And we saw that variance is defined as the summation of squared deviance from the mean divided by n-1 in the case of a sample. But sometimes you may have data in a tabular form or as a frequency table. And the idea of calculating variances and even the mean is very similar, but there is just some slight difference. And this concept is also used in finance, where instead of a series of occurrences, you may be given maybe probabilities of likelihood of a certain outcome happening for a given stock. So we call it expected expectations, and the expected value would be that probability times the return that is supposed to be accruing if that event happens. So the idea is very similar to the frequency tables that we looked at in the prior video. And you also may be given grouped data, where instead of having individual data points, you may be told that maybe there are 10 observations between the values 15 to 25, then there are 5 between 25 to 35, and so forth. So we can calculate or we can approximate mean and variance in a group data, but we can also work with tabular data, and we see that the calculations within tabular data will be similar or same as what we would do had we been given the individual data. So let's illustrate this with an example. So let's say we have a tabular data or frequency table for age distribution of players in a certain team. So instead of having raw data, we're told that we have 2 players whose age is 21, and then we have 3 whose age is 38, and so forth. So, and we want to calculate the average age as well as, assuming this is the sample, we'll look at the sample standard deviation and sample variance, which we will all derive from here. So to calculate the mean, we will be essentially, it is like the weighted mean concept, where the weights now are the frequencies. So we will be multiplying each age with the number of observations of that age. and then we'll add up that product, and then we will divide it by the total count or the sample size n. So this is essentially like the weighted mean. It's a way to find the mean where we're doing fi, the frequency of each cell, times xi, the observation corresponding to that cell. And we're summing it and then dividing it by summation of fi or n. So to calculate the numerator, so first let's calculate the mean. Mean is again given by this times this times this, so which is like sum product. So I can use the Excel function sum product. What sum product will do is it'll do row by row multiplication and then add up our columns. So it's going to look at these two arrays. It's going to multiply the first element of array 1 with the first element of array 2 plus the second element with the second element and so forth. So this is essentially giving us our sum, and we divide it by the sum of our observations. So we can look at the sum of this column, which is our frequency distribution. And we get that the average age is 30.68. Now, the formula for standard deviation is essentially we calculate the deviation from the mean, and then we multiply it, we square it and we multiply it by the frequency. So we'll still be doing the deviation like we would have done in the calculation of standard deviation. So xi minus x bar, where we just calculated x bar, we square it and then we multiply it with our frequency. And then we will divide our answer with n minus 1. So to calculate our squared deviation, we will look at our xi minus our mean, and because I'm going to be dragging it down, I can hit F4 to anchor it. And we'll put this in parentheses. We will square it. So these are our squared deviations, and we can drag this down. We get our xi minus x bar squared for the entire series, and then we will multiply it with the frequency. So we will do our frequency times our squared deviations, which again we could have done some product, but I just want to illustrate how this formula works. So we are multiplying this, and this is our squared deviation times frequency for each observation. Then our variance is essentially our sum of squared deviation, so we can do the sum here. Divided by our n minus 1. So to get my n, I first have to take the sum of my observations. I could have done that initially. So this gives me how many data points do I have in my overall data, then minus 1. Then we get the variance. So our variance is 37.14333. So our age variance is 37.14333, and our mean is 30.68. Now these numbers are identical if we had been given raw data. So if this is the raw data, we can easily calculate mean in Excel. It's given by the function average. So I type average of this series, and we get 30.68, which is what we had gone had we just been given the table. And then we can also calculate this variance. And we're assuming this is the sample. So we will do variance.s. there are two variances, variance.p for population, variance.s for sample. We look in the sample variance, and double click this, run this series, and 37.1433, which is what we had got here as well. So the frequency table way of calculating mean and standard deviation and variances is the same as what had we gotten raw data. Again, the square root of variance is standard deviation. Now the advantage of this method is that we can apply this to grouped data also. So let's say we were given a grouped data like we had 0 to 2, then 3 to 5, 6 to 8, 9 to 11, 12 to 14 as the intervals or groups. And we were given the frequency of occurrences in each group, that we had one observation in this group, we had 10 observations in 6 to 8. So how do we calculate the sample standard deviation variance as well as the sample mean from this group table? Well, we do not have individual values, but we can use the method we did before, this method, to get an approximation for it. So what we do is that we calculate the midpoint of each group, and we pretend that that is this value. So we will do the same analysis. We'll be now multiplying our frequency with the midpoint, and then doing a sum product, and then divided by our sum of frequency to get our mean, and then we can apply the same method to get the variance. So these will not be exact because we do not know the actual data points, but these will be a good approximation of the actual sample variance and sample mean. So again, the frequency table method helps us with grouped data, and also when we have expectations, we can calculate expected values, and we can find the mean and standard deviation using those methods, as we'll see later on.